Okay, so these are questions number 36 and 37 of the Magnetic Fields homework booklet. So in question 36, we're given a circuit, which is this diagram down here. And what we've got is we've got a DC supply, so we've got a DC cell connected to a switch and a variable resistor, and then that is then connected to a coil of wire that goes around this soft iron core. So on this side, we're basically creating an electromagnet. On this side, we've got a coil of wire just connected to an ammeter, so we've got a complete circuit. So what we've basically got is we've got a transformer that's taken the energy on this side and transferring it to this side, so we end up with an induced EMF and a current on this side, provided that there is a change in the magnetic flux magnetic flux or magnetic flux linkage on this side. So what we're told is that when the switch is closed, a small current passes through coil X. So there's a small current going through here, and that the current is slowly increased by using this variable resistor. So the resistance of the resistor goes down, so the current gradually, very slowly goes up. The current then reaches the maximum value, and then this is switched off, so the switch is then opened again. We want to know when the reading on this ammeter was basically the biggest. So we want the maximum reading on the microammeter. So what we need to think about is we need to think about how the magnetic flux or the magnetic flux linkage from this side is changing, because we only get an EMF induced on this side if there is a change in magnetic flux linkage on this side. So when this thing is first turned on, and there is a very small current going through it, because this is a DC supply, once the current's turned on and there's a current going through it, the actual change in magnetic flux linkage is zero, so nothing happens. So basically it would be zero, so the zero starts here, and so the flux would basically, there would be no change in the magnetic flux at all. And then as you gradually change the resistance of this thing so that the current goes up, as the current gradually goes up, then the magnetic flux linkage or the magnetic flux would gradually go up. So it would change. So there would be a small EMF induced here until it got to the maximum value. And then what would happen is when you open the switch very quickly, the magnetic flux linkage here would go from its maximum value down to zero very quickly. So it would do that. And then the current would be zero, and there would be no magnetic flux linkage at all, because this thing's then gone. So what we need to think about is, because the EMF, which generates the current on this side, is equal to the number of turns on this side multiplied by the change in magnetic flux, or the rate at which the magnetic flux changes, we basically want to know when the magnetic flux changes the fastest, because if that'll give us the biggest EMF, and if the biggest EMF will give us the biggest current. So if we look at A, when you've got a small current flowing at the start, especially if this is a DC supply, so when the small current's flowing at a constant value, there's no change in this magnetic flux, so the EMF is zero. So that will give you a zero on this side. When the current's increased, it says in the question it's increased slowly. So there is a change in magnetic flux, but the rate at which it changes is very slow. So you'll get a really small EMF induced. The current is then switched off. So the magnetic flux is at its greatest value on this side because the current's biggest. And then when you suddenly turn it off, it will drop down to zero incredibly quickly. So the biggest change in the magnetic flux is when this thing is turned off, because it goes from its maximum value down to zero very quickly. So the rate at which that happens is big, and so you get a big EMF. So therefore the answer is C. When the current is zero, you basically don't, the current is zero on this side, which means that there's zero EMF on this side because there's no magnetic flux at all on here, so you don't get a current. So therefore your answer to this one is C, simply because you get the biggest change in magnetic flux on the left hand side when you turn this thing off. For question number 37, what we have is we've got a transformer that's got 1,150 turns on the primary coil. It's got 500 turns on the secondary coil. We've got a primary coil that draws a current of 0.26 amps from a 230 volt supply. So again, draws basically means it takes this current from this particular supply. And the current on the secondary coil is 0.50 amps. We want to know what the efficiency of our transformer is. Now, the efficiency is equal to the power going out divided by the power going in, which is equal to this equation here, because the power out is equal to the current out multiplied by potential difference out, so that's the current and potential difference on the secondary side, divided by the current in multiplied by the potential difference going in. So that's the current and the potential difference on the primary side. Now we know some of these numbers, but we don't know all of them. What we don't know is we don't know what the voltage going out is. We know the current going out because it tells us there. We know the current going in because it tells us there. We know the voltage going in because it tells us there. But what we don't know is this V0. So then we have to work this out. But what we are told is we know the number of turns on this thing. And we know that for using our transformer equation, this equation here, the number of turns on the primary coil divided by the number of turns on the secondary coil is equal to the potential difference on the primary side divided by the potential difference on the secondary side. So if we just rearrange this for the potential difference on the secondary side, which is the voltage going out of our transformer, this V0 here, that's just a matter of putting these numbers in. So the voltage on the primary side is 230, the number of turns on the secondary side is 500, and the number of turns on the primary side is 1150. So the secondary voltage is 100 volts. So we then take this and we can put all four of our numbers into this equation here. So our current going out is 0.5 amps. The voltage going out is 100 volts. We've just worked that out. The current going in is 0.26 amps. The voltage coming in, so it is 230 volts. And if we do that, we get 83.6 as our answer. If we multiply this by 100 to get it as a percentage. So therefore, the answer is C at 84%. So they were questions number 36 and number 37 of the Magnetic Fields homework booklet.